In this video, we're going to learn how to find the derivatives of the three most common inverse trig functions, arcsine, arccos, and arctan. So in each case, we're going to do a full derivation using implicit differentiation, and then in future videos, we'll look at how to use these results. So let's start with finding d by dx of arcsine x. So the trick here is to start by writing y equals arcsine x. Now, it's a very subtle change here, but there was no y originally. The challenge is to just differentiate arcsine x. Introducing a y helps us out because we can do sine of both sides, giving me sine y equals x. Remember, by definition, sine of arcsine x is just x, because arcsine is the inverse of sine. Now we can differentiate this using implicit differentiation, because the derivative of sine y with respect to x is cos y times dy by dx. The derivative of x is just 1. So we have our expression for dy by dx, but it's in terms of y. dy by dx is 1 over cos y. But we want the derivative in terms of x. So how do we express cos y in terms of x? Well, we go back to sine y equals x, and we can say that sine squared y is equal to x squared, and then sine squared y is 1 minus cos squared y. So 1 minus cos squared y is x squared, and therefore cos squared y is 1 minus x squared. And that means that cos y is, well, it's the square root of 1 minus x squared, but it's really plus or minus root 1 minus x squared. So which are we using? Are we using the positive or the negative? Well, there's a couple of ways of thinking about this. Both of them kind of rely on the graph a little bit. If you think about what the graph of arcsine x looks like, maybe you haven't thought about this for a while, but it's a rotated, or reflected rather, sine graph. It looks like this. So one simple point to make is that you can just see the gradient of this is always positive. Okay, it's never got a negative gradient, which means we'll have the positive version of root 1 minus x squared, and we get 1 over positive root 1 minus x squared. Now, that's fine. Another way to think about it is to say, well, what can we say about sine y? Well, the y values in question are y values between pi over 2 and minus pi over 2. That's just the y values of the arcsine graph. Well, what can we say then about cos of any values between minus pi over 2 and pi over 2? Well, they're always positive, right? If you think about the cos graph, it is positive in the interval minus pi over 2 to pi over 2, and therefore cos y must be positive. So look, here's dy by dx, and therefore d by dx of arcsine x, with no reference to y needed anymore, d by dx of arcsine x is 1 over root 1 minus x squared. Okay, let's work through the other ones. So d by dx of arc cos x. We'll do something very, very similar. We'll start with y equals arc cos x. Then we'll have cos y equals x. And we will differentiate. So the derivative of cos y is minus sine y dy by dx. Derivative of x is 1, so we have dy by dx is minus 1 over sine y. And we just do the same trick that we did before. So we have cos y equals x, so cos squared y is x squared. So 1 minus sine squared y is x squared, and therefore sine squared y is 1 minus x squared. And once again, we've got this thing where sine y is plus or minus root 1 minus x squared. And so a quick think about which one it is. Same thing we can do, which is to think, what does the graph of arc cos look like? And it looks like this. So it's again a reflected cos graph on a particular interval. So we can see that the derivative of that is always negative. So we've already got a -1 here. So we actually just want -1 over something positive. So root 1 minus x squared. That guarantees the derivative is always negative. The other way to think about it is to say that we always have y values between 0 and pi, and sine of numbers between 0 and pi are always positive. So -1 over something positive gives us our negative gradient. So here's our answer. D by dx of arc cos x is -1 over root 1 minus x squared. Now, what's really nice about this, and just kind of quite cool, is that the derivative of our inverse trig function is not a trig function. That's quite neat, actually. That it's unexpected. We normally think, well, any trig term will just differentiate or integrate to more trig, and yet what we found is a function here that is the derivative of a trig function, albeit an inverse one, but it itself is not a trig function. Okay, finally arctan. This is probably the neatest one. Again, y equals arctan x, then tan y equals x. So the derivative of tan is sec squared. So we have sec squared y dy by dx equals 1. So dy by dx is, well, you might be tempted to multiply both sides by cos squared y and have cos squared y, but actually leaving it as 1 over sec squared y is clever, because sec squared y is 1 plus tan squared y. That's just an identity. Tan squared y, well, that's x squared, right? Because tan y is x. So what we have is dy by dx is equal to 1 over 1 plus x squared. So a really neat little result there. So d by dx of arc tan x is 1 over 1 plus x squared. So there we've got it. 3 derivatives of our inverse trig functions. Derivative of arc sine x is 1 over root 1 minus x squared. The derivative of arc cos is just the negative of that, -1 over root 1 minus x squared. And for tan x, it's 1 over 1 plus x squared. Now that we've derived all of those, let's use them in the next video. See you there.